All right, so in this one, we have a position time graph for a particle that moves in a straight line under uniform acceleration. And it wants us to do A, B, C, D, E, and F. If you need to pause, read. So here we go. Here is an x of t graph. X for position, t here is time on the horizontal axis. So let's do it. Part A asks us to draw the motion diagram, which is not bad at all. But in order for you to draw the motion diagram, you have to be able to look at a graph and kind of see what the object or particle is doing. So I'll teach you how to look at this stuff real quick. So the first thing I notice here is that the graph here has the y-intercept at about -5, right? There's that dot right there. And then here is the black dot, here's the vertex, and that's at 6 and -23. So essentially, this is how you interpret this information. Well, how do you know if an object's moving left, right, or stationary to begin with? All you have to do is look at the graph. So the first thing I want to look at the graph here is this particular concept, a tangent line. The tangent line of an xt graph tells you your instantaneous velocity. And then if the slope is steep, it moves fast. If the slope is gradual, then it moves slow. So how do you know if there's a slope to start? Well, go back to time is equal to 0. So according to this graph, time is equal to 0 is right there. The graph intercepts there. So all I'm going to do is I'm going to suggest that you just extend this line. Okay, kind of visualize it. Extend this line past the x-axis here, or the position axis here, or the vertical axis, I should say. And if that slope exists, then you would say that it's moving to begin with, right? Don't just assume that the object starts at rest. Well, if you look at this line that I just drew, the tangent line, that tangent line exists, and that is a negative tangent line. And so therefore, I want to make the safe assumption that it is moving in the leftward direction to begin with, right? So the fact that there is a slope tells you it's moving. Well, the slope is negative, so that tells you that it's moving leftward to begin with. So here in my work, I have a negative VI just to help me visualize what's going on. Now, as I draw more tangent lines along this first segment in the curve, I notice that the slope keeps getting more gradual, right? Well, what does that mean? As the slope gets gradual, that just tells you that the object is slowing down, right? The steepness of the slope tells you if it's moving fast. Well, in this case, from 0 seconds to 6 seconds, the slope keeps getting flatter and flatter and flatter. Eventually, it gets flat at 6, which tells me that the object is initially moving leftward and slowing down and comes to a stop at 6 seconds, right? So therefore, visually, I'm just going to draw an arrow pointing left. That's my VI. And then as time increases from 0 to 6 seconds, these arrows that represents V keeps getting shorter and shorter, and eventually it comes to a stop. Well, it comes to a stop at 6 seconds because the graph said so, right? Well, what does it do after that? I'm just going to draw more tangent line. So the tangent line that just came up now, well, this tangent line is now in the positive direction. This is a positive slope. So therefore, I'm going to say that V is now positive. Well, what does that mean? It just means that the object just turns around. As you draw more tangent line, like I do here, you notice that the steepness of these tangent line keeps getting steeper. Well, if the tangent line gets steeper, it tells you that the object is speeding up in that direction, right? The steepness tells you whether it's moving fast or slow. Well, at 6 seconds, the tangent line is flat, and then as I draw more tangent line, it gets steeper and steeper and steeper, which tells me that it turns around and now it's moving in the rightward direction, and with increasing speed or increasing velocity. Okay, so these arrows that are coming up, they keep getting longer and longer because the velocity keeps getting faster and faster. So that's the schematic for part A. Now let's do part B. Part B asks us to find the initial velocity at time equal to 0. Well, once again, as I said earlier, don't just assume that VI starts at 0. In order to safely assume so, just draw a tangent line. If your tangent line is flat, then it's most likely 0. If the tangent line, like this one here, is a negative slope, then you would say that it's initially moving in the leftward direction. So I think the quickest way to find part B is just to use the two average velocity functions. So here I have delta x over delta t is equal to vi plus vf over 2. But you notice here I'm actually going to go ahead and pick 2 points that's I think is easiest to do. Right? I know that at 6 seconds the object comes to a stop. Well, it was initially moving in the leftward direction at 0 seconds. So here, by just kind of focus on the information in this little dashed blue box that I just have here, I think it just makes your life super easy to do. Well, in order to find VI, I need delta x. I know time already. Time here is just going to be 6 seconds because I'm just going to go from 0 to 6 because it comes to a stop. So that's just moving the leftward direction. Okay. So if I pick that data set, my VF is going to be 0 at 6 seconds because it comes to a stop before it changes direction. Well, what's my delta x? Delta x can be broken up into xf minus xi. And really from here, you just look at the graph, right? Well, what is your xf? According to this point here, 6, negative 23, at 6 seconds, if you go across, right, it's below negative 20. So it's going to be negative 23 because the vertex here is given. Well, what's your xi? Xi here is negative 5. So I'm just going to go ahead and visualize these two blue lines, and I'm just going to draw an arrow. So it starts at negative 5, and then it ends up at negative 23, meaning it moved leftward, 18 spots. So just basic math, 5 to 23 is 18, and it's moving leftward because the arrow here is moving down, okay? All right, other than that, if you want, you can just plug in values. Here, xf is negative 23 because the graph said so, minus, but don't forget that xi here is itself as a negative quantity, okay? So xi starts at negative 5 for this particular graph, and then a negative makes a positive, so negative 23 plus 5 is negative 18, and negative 18 divided by 6, which is 3, and then you multiply this 2 across. So if you want, just finish the math on your own, and that should come out to be negative 6 meters per second, which makes sense because initially we established that this is a negative tangent line to start, and if it's negative, therefore it's moving to the left. So in this case, the object is essentially moving leftward at a rate of 6 meters per second. So that's the answer to part B. Okay. All right, let's do C. It says calculate the particle's acceleration. Well, to calculate the particle's acceleration, I can just use the change in velocity over change in time. So here, well, I think it's super easy to do because once you have VI, VF here is 0. Because again, I'm just going to focus on my attention between 0 seconds to 6 seconds because the problem says that this particular particle accelerates uniformly for the whole entire graph, right? So it doesn't really matter which points you pick, the A will come out the same. But I'm just going to use these 2 points because I think it's just quick to do. So I'm going to start at 0 seconds and I'm going to go all the way to 6 seconds. Well, at 0 seconds, the object is initially moving at a rate or at an initial velocity of negative 6. And then VF is just 0 because at 6 seconds it came to a stop. So here, the negative sign gets carried down. VI itself is a negative quantity, so I put that in parentheses. So a negative and a negative makes a positive 6. And then, well, how much time did it take to occur? Well, again, I'm just focusing on from 0 to 6 seconds here, so the change in time here would just be 6. So 6 divided by 6 will give you 1 meters per second square. And here I highlight the positive sign because it says acceleration, and acceleration is a vector. So therefore, that is our answer for part C. So pretty light work. I think for you to crack these problems out, you just have to decide which data points to pick. And I think if you pick wise points, it'll make these parts really easy to do, okay, and fast to do. All right, let's go ahead and move on to D. Here, D asks us to find two things: average speed and average velocity between 0 to 10. So the first thing I do want to point out is that average speed and average velocity will be different for this particular time interval because from 0 to 6 seconds it was moving leftward, and then from 6 seconds on to 10 seconds and beyond that it changed direction and it moved rightward. So anytime an object changes direction, the average speed and average velocity will have different magnitudes. Okay, they'll have the same magnitude if it moves in one direction, but in this case, just from the graph itself, we noticed that it was moving leftward and then it stopped and then it changed direction. Therefore, these two quantities would be different. All right, so let's go ahead and crack out average speed. Well, to do average speed, we need distance over time. Well, how do you find what the distance is? Literally just count how many steps it moved left and how many steps it moved right and just add it up. So here, I'm going to start once again from 0 seconds here because the problem here, it starts at 0 second and goes to 10. So I'm just going to put a couple dots here or a couple data points here. So here, this is 0 and negative 5, right? 0 because it's 0 second, and then negative 5 because it intercepts here at negative 5. And then if I'm looking at 10 second on the graph, it looks like, it's about 10 horizontally, right? Because 10, you go down and it sits on the graph there. And then if you go across here, this is negative 15 because it seems like each of these boxes is negative 5 or just 5. So it'd be negative 5, negative 10, negative 15. Now go across there. That's what the dot would be. Now I highlight negative 15 because the graph seems like it intersects at that corner nicely. However, I don't want to just assume it's negative 15. So I'm just going to prove that it's negative 15 just to be safe, okay? Well, how do I know if it's negative 15 for sure, right? Visually, it looks like it's at the corner, but I'm just going to go ahead and prove it just to make sure that I'm not goofing. So here, I'm just going to apply my displacement function, which is vit plus 1/2 at squared, right? And I'm just going to go ahead and expand displacement into xf minus xi, and then I'm just going to move xi to the other side, okay? Because I'm trying to find out what the position is at 10 seconds. So here, if you are clever, you can just plug in all this calculator work. Vi here already found is -6. You know, don't get sloppy about sign. The initial velocity in this case at 0 seconds is, you know, -6. Well, how much time? Well, the time would just be 10 seconds because it says from 0 to 10, right? And this is 1/2. That's part of the function. A is a +1, and then t here is 10 square, and then add. But keep in mind, this way if you're sloppy, you'll get goofy. Xi itself is a negative quantity, so plug in -5. So if you clean all this up on your calculator, you'll get -15, right? Because this first term is -60, the second term is a +50, and then this last term is a -5, so -60 plus 50 is -10, and then -10 plus -5, which is -15. So it is indeed on that particular point, all right? So don't just assume if you want, run a test, just in case, you know, it's a close point that you're like, is it about? So if you're eyeballing, it's fine. If you're looking for a exact value, run a test. All right. So here I'm just going to put this particular line here because I know that it's moving leftward from 0 second all the way to 6. So how far is that? That is going to be a distance of 18 or a -18 for displacement, right? So it went from -5 to -23, which is 18 spaces. And then that takes 6 seconds. But then at 6 seconds, it turned around and it starts to accelerate to the right. So from 6 to 10 seconds, I need to find out how far it went. Well, from just the graph itself, I can count real quick. So this, where my cursor is -23, and then it went all the way up to -15, or it went to the right to position -15. That would be 8 spots, right? So it went leftward 18, it went upward 8. So if you count, you know, that's 18 plus 8 because distance is a scalar, so we just add all the distances up, and then the time interval would just be 10 because it's dictated for us here from 0 to 10, and that's it. So 18 plus 8 is 26. 26 divided by 10 is 2.6 meters per second, and then speed is a scalar, so you don't need any directions. All right, now let's do average velocity. Well, to find average velocity, essentially you're just trying to find this particular slope, right? Average velocity is just the slope between the starting point and the ending point. So in this case, average velocity here is just displacement over time. So I'm just going to use xf minus xi divided by t, and then just plug in values. Well, what's your xf? Your xf is -15 as I proved. And then what's your xi? Well, your xi is given in this particular problem. It intercepts at the y or at the vertical axis here at -5, which is given to us. So xf is -15 itself minus, but xi is another -5. So negative and a negative makes a positive. So -15 plus 5 gives you -10, okay? And it will be -10 divided by 10, which will leave you with -1 meters per second. So the average velocity in this case will be -1 meters per second. All right, that's it. And it asks for velocity, so I'm just going to put the negative sign because it is a vector. All right, let's go ahead and crack out part E. Excuse me. E and F here. It says, what is the object's instantaneous velocity at 15 seconds? So this one's pretty light work to find instantaneous velocity. Again, using the average acceleration equation for this particular problem because it's uniform acceleration. We can find Vf here, or V instantaneous is equal to the acceleration times time plus Vi. So here, I'm actually just going to start at 6 seconds. I'm going to start at 6 seconds because at 6 seconds, the Vi here is 0. Okay, so I know the object stopped at 6 seconds and then it accelerates to the right afterwards. Well, if you look at part E wants 15 seconds, which means it's already moving rightward. So instead of starting at 0 second, I'm actually just going to start at 6 seconds, only because I know at 6 seconds it was at an initial well, it was at a stop. It was at a momentarily stop, right? Because it came to a stop before it changed direction. So therefore, what's my A? My A is just 1 because I already calculated that earlier. Well, what's my time? You notice here my time is just 9, okay? Because I'm starting at 6 seconds. From 6 seconds to 15 seconds is a difference in 9 seconds, okay? So therefore, my VF at 15 seconds is a positive 9 meters per second, and I highlighted the plus sign because it says instantaneous velocity, which is a vector. So in this case, we will say at 15 seconds, it is moving rightward at a rate of 9 meters per second. That's it. Again, if you want to, you can you go from 0 to 15. Okay, so I'll do that for you just in case I just lost you there. It's about picking points that are clever, that just makes your life, I think, easier to do. Now, same part, except if you wanted to go from 0 to 15, well, just be consistent. Your A is still 1 for the whole entire problem. Time here is 15 seconds. But if you go back, to 0 seconds, well, what is your VI? Your VI was -6 meters per second. So as you can see here, 1 times 15 is 15, and then 15 plus a -6, which will give you the same answer, a positive 9 meters per second. Okay, so whether you choose to use the vertex where I know V is equal to 0 and just go from there, from 6 to 15 is 9, or you can go all the way back to 0 second and go to 15, right? That's entirely up to you. Okay, all right, that's that. Almost done. Part F. Part F asks us, when will the instantaneous velocity equal to the average velocity between 0 to 15? Well, instantaneous is a single tangent line. Average velocity is the slope between 2 points, right? So essentially it's asking us, when will these two slopes equal? The tangent slope and the slope of 2 points. So in order to do so, I'm just going to go ahead and drop a little dot there, because here it says from 0 to 15, and then the other dot is going to be right there at 15 seconds. So at 15 seconds, go up, that's where it is. I mean, it looks like, eyeballing it, it looks like it, what is that, 5, 10, 15, like maybe 17 and a half, but we'll go ahead and do it, right? So eyeballing it, you can kind of know roughly about the position at 15 seconds, but we'll do this properly, okay? Now, that is average velocity. This black line that just came up, right? Because it connects initial and final position. All right, so average velocity by definition is the change in position over the change in time. Okay. However, I do want to point out, if you are thinking about what information you have already, to find average velocity for this interval is pretty light work. Okay. Well, there are two functions you can find average velocity with when A is constant, and I can apply this for this problem because it says A is uniform. Or you can apply this function here, right? Displacement over time. As I stated earlier, if you want to, you can roughly eyeball it, and then say X at 15 seconds, it's about 17 and a half. However, I don't need to eyeball it. I can just use this function on the left here. I'm just going to use VF plus VI divided by 2 because, well, I already know all this information, right? At 15 seconds, we just calculated it's 9 meters per second, right? So watch my cursor. I already found the velocity at 15 seconds, which is 9. Well, what's my VI? My VI over here at 0 second was -6. So I can just do 9 plus -6 divided by 2, and then that'll give me 1.5 meters per second. So I'm just trying to make a point here. If you hone into the information you have already, it should make some of these parts super fast to do, okay? If you want, you can go find delta x. You can find xf and then minus xi, which is given to us as -5, and then divided by the change in time, which is 15. You should try it out if you have time, or you can just do this and then just call it a day. So if you have time, practice the other strategy, and it should give you 1.5 meters per second, positive and all that good stuff. So I'm just trying to make a point here, okay? So here, the proper way to express this would be positive 1.5 meters per second. It's positive because this black line has a positive slope. So that's that, okay? Now, so that's the slope there, right? The slope is positive 1.5 meters per second. Even though I didn't put a positive sign, the slope itself is moving, from left to right, is moving upward, okay? Now, well, it wants us to figure out when will the instantaneous velocity equal to this, right? So at what time will VF be 1.5? So all I have to do is set up, again, my VF function, or my V of t here. V of t is the same as VF, which is equal to AT plus VI. And then, well, we know VF is 1.5 because the problem states, when will VF be V average? We just found V average, therefore V average is now VF. So instead of VF, we can substitute that in for 1.5. A is known, we already found that earlier. Well, t here is our unknown because it's looking for when, which is our t variable. And then VI here is -6 because the problem dictates the interval of time for us. It sets from 0 to 15 seconds. So VI would have to occur at 0 second, which is -6 meters per second, as we found in the first part of the video. So we need to rewind it, okay? So -6 was calculated earlier, 1 meters per second squared is calculated earlier, 1.5 we just calculated, and then the only thing here, as you can see, is just our t. Well, to get t by itself, I'm going to move this -6 to the left side. Okay, so -6 moving to the left side, it changes sign, so it becomes a +6. 1.5 plus 6 is 7.5. And as you can see here, even though this is 1 meters per second square, it really doesn't do anything in terms of multiplying. So really t is just equal to 7.5 seconds. Okay, so this particular quantity, Vf, will equal to V average during this interval at 7.5 seconds. Okay, now essentially if you visualize it, watch this black line that I have. Okay, so this black line that I have connects 2 points, right? It connects the position at 0 second, and it also connects the position at 15 seconds. But if I can just move this graph down, you notice there, I haven't done anything to the slope. I just drew the same slope, except I just shifted down the graph, right? So as you can see, it touches this, about this point here on the graph, aka this tangent. So this black line touches a single point on this curve now, and that's called a tangent line. Well, where and when does this occur, right? This occurred roughly at about 7.5 seconds. So if you look at the horizontal axis here, this is 5, that's 6, that's 7. Well, that's 8, so it's between 7 and 8. So you can say that this particular phenomenon occurs at about 7.5 seconds just by drawing a tangent line there, and you can eyeball it. So therefore, I know my answer is on. Okay? All right. I hope that helps. Stay nerdy. Don't be whack.